Okay. Collisions. Bang. What do you think about this? Well, since our operational definition of what a force is, let's say, since a force is one interaction between two objects. This is Newton's third law, really. Newton's third law, since force is one interaction between two objects, that means the force on object 1 from object 2 is equal but exactly opposite in direction to the force on object 2 from object 1. Right? It cannot be otherwise because Newton's third law, and if we really want to, this just falls right out of what our definition of a force is. If a force is one interaction, then this has to be true. You can't have the two different things experience a different amount of force if there's only one interaction. So, also note that the time of the interaction is the same for both objects, right? Like object 1 can't be interacting with object 2 for a second, while object 2 is interacting with object 1 for like only half a second. The duration of the interaction, just like the force, has to be the same for both. Time of the interaction is the same for both objects. So that means that if we had like a force versus time graph, could look like this. So we have force on this axis and time on this axis. So let's say the interaction maybe looks like this. Let's say that's the force on object 1. This is time here. Then the force on object 2 is exactly the same, but opposite. How'd I do there? Pretty good. So those are equal areas, but of course calculus-wise this is underneath and that one's above, and they're opposite to each other, so that would always be the case. And that means that the integral from time whatever to time whatever, the duration of the interaction, f1 dt is equal to the opposite that, right? That has to be true. Sorry about the smudgy there. It's an arrow. Looks like an F, doesn't it? That's no good. There. All right. Well, this is impulse, right? So since the integral of force with respect to time is equal to, that's impulse, and impulse is equal to change in momentum, that means that here, this is the change in momentum of the first object, and this is the change in momentum of the second object. All right, well, this is kind of a big deal here, so what's this mean? There's a lot of different ways you can write this and interpret this. One of them would be to say that the change in momentum that the total change in momentum is 0, right? Because you could add that to the other side. Then you have the change in momentum of 1 plus the change in momentum of 2 is equal to 0. So you could say that the sum of all the change in momentum is 0, or momentum is conserved. Now, when is it conserved exactly? Well, when you have two objects that are free to interact with each other. Like, for example, if you take a rubber ball and you throw it against a concrete wall, momentum is not conserved because the wall is fixed in place. It's not free to move. If you have two objects that are free to move, then and they interact with each other, then momentum is going to be conserved. Another way to write this is that, let's flesh this out a little bit. So the change in momentum 1, that would be delta m1 v, and this is delta m2 v, where the v's, it's just taken without subscripts, that means the velocity of that particular object, right? So we're not going to like multiply the mass of object 1 by the velocity of object 2. That would be crazy in not a good way. Let's see, that means change in is just final minus initial. So that's m1 v final minus m1 v initial. Again, that's just taken for granted that whenever we multiply mass times the velocity, it is the velocity of that object, is equal to, oh, I forgot my minus sign there, right, minus m2 vf minus m2 vi. And if we kind of shuffle things around a little bit, algebra-wise, and we decide that we don't like negative signs, if we can avoid them, then we could have here, this is plus over here, and this is my, so let's leave the, so if I left the initial over here on this side, it would be positive, and then if I added that over there, then I'd get m1 times its initial velocity plus m2 times its initial velocity. And then if I move this one over here, you can check all the signs. It's just algebra that I'm doing here. And this is a really interesting form of this too, because this says this is like the total momentum before, and this is the total momentum after. So here I'm not doing, it's different than this, because this was all of the momentum. This is the momentum, change in momentum of object 1. And this here, this is the total momentum of both of the different objects. And if you do that before and after, it's got to be the same. Of course, if we understand that there's no change in momentum, then this also, just concept-wise or intuition-wise, that should make sense. So the total momentum before equals total momentum after. Boy, is this a powerful problem-solving tool here. There's a couple more things I need to tell you. You can test this out for yourself. A couple definitions. Definition. An inelastic collision is an interaction where the two objects they may, well, let's say, I'm saying this in a little bit of a clunky way. An inelastic collision is an interaction where, let's say this, where kinetic energy is lost. a completely inelastic collision is an interaction where the two objects stick together. Two objects stick together. This happens a lot. There's any number of examples I can think of. There's the classic kid runs and jumps onto a skateboard, or person runs and jumps into a boat, like that's sitting there on the water and they're running off of a dock or something like that. Or there's something that you're going to see in classic momentum kind of problem called a ballistics pendulum, where there's a block of wood and a bullet or some kind of projectile is fired into the block, and it sticks into the block, and then the block swings up, and you can use data about what the block does to figure out how fast your projectile was going before it hit the block, without having to have some super high-speed trick photography or whatever. And this is an inelastic collision. This is a completely inelastic collision. And then, of course, that means an elastic collision. That should make you think bouncy, bouncy. Is an interaction where kinetic energy is conserved. And boy, you have to watch out for this. This is one of the College Board's favorite little things to do. If somebody says, if you read those words, elastic collision, you better immediately think, oh, I'm going to have to use the fact that kinetic energy is conserved. Momentum is conserved in all of these. It doesn't matter. Momentum is conserved. Set off your screen. All right, so I think it's time for you to try some problems. You can work along with the video that I make for these first problems and try out some conservation of momentum.